Hello everyone, welcome to the talk Perturbation Resilience of Non-Uniform Case Center. My name is Sayan Bandyopadhyay and I am a postdoc at the University of Bergen. Let me start with the definition of the non-uniform case center problem, which is a geometric clustering problem. In this problem, we are given a set of points in some metric space. You can think of the Euclidean plane for simplicity. And here the task is to partition the points into k groups or clusters such that each cluster contains similar points. And here the notion of similarity is captured by the balls. So a cluster must be contained inside a ball. Let me formally define this problem. In this problem, we are also given k integers r1 up to rk, which are called the radii parameters. And here the goal is to find k balls of radii alpha r1 up to alpha rk, so that the union of these balls should contain all the points and the value of alpha is minimized. The clusters are induced by the chosen balls in the natural way. If a point is contained in multiple balls, then it is assigned to one of them. And in this figure, I have shown the 5 clusters by 5 different colors. NUKC is a generalization of the classic K-center clustering problem, where all the radii are the same. In many applications, we need to consider non-uniform radii to retrieve the natural clustering. For example, consider the dataset on the left. Here, if we apply K-center clustering, we get the clustering shown in the middle figure. However, this clustering is not the natural clustering of the dataset. If we apply non-uniform K-center instead, then we can exactly retrieve the natural clustering. And this is shown in the figure on the right. In this work, we consider an alternative formulation of the problem, which is defined in terms of number of distinct radii parameters given to us. So in case of K-center, we have a single radius parameter, and one can extend it for 2 radii classes where we have 2 distinct radii parameters, R1 and R2, and multiplicity parameters K1 and K2, such that K equals to K1 plus K2. And here we would like to select K1 balls of radius alpha 1 and K2 balls of radius alpha 2. And one can naturally extend it to T radii classes where we need to select Ki balls of radius alpha I. For the rest of the talk, I will stick to this formulation of the problem. Let me talk about some previous works of this problem. So in this special case of K-center, approximation algorithms are known with 2 approximation factor. And these approximations are tight in the sense that it is NP hard to obtain any better approximations. And all these results are classic results from 80s and 90s. Compared to this, NUKC was formulated very recently by Chakravarti et al. And they considered the approximability of this problem and showed that the problem is hard to approximate within a factor of lambda for any value lambda. However, they obtained a bicriteria approximation. In particular, if we are allowed to use a constant times Ki balls instead of only Ki balls for each radius class I, then we can obtain a better or improved constant approximation. They also studied the 2 radii class version of the problem and they obtained a true constant approximation. However, even for 3 radii classes, no approximation algorithm is known. In this work, we consider NUKC through the lens of stable clustering. So in stable clustering, we assume that the clusters are well separated from each other or distance-wise far away from each other. So one might ask, what's the reason behind studying such a simple model? So in clustering, there is a very interesting phenomenon. So in clustering, theoreticians and practitioners do not share the same view. Theoreticians think that the clustering problems are extremely challenging problems and they are computationally hard problems. However, practitioners have observed that on most of the real life data instances, one can solve the clustering problems very easily. Now, the question is, what's the specialty about the real life instances? And researchers have tried to address this issue by modeling real life instances through different models. And stable clustering is one such way to model the real life instances. And there are different notions of stability available in the literature. Here we consider the more popular perturbation resilience, which was introduced by Bilu and Linial in the context of maximum cut. In the context of a clustering problem, an instance is called good or psi perturbation resilient for some positive real number psi if two conditions hold. The first one is that there is a unique optimal clustering corresponding to the instance. And the second one is that if I perturb the distances of the instance by a factor of psi, or if I increase or decrease the distances by a multiplicative factor of at most psi, then the optimal clustering does not get changed. So the optimal clustering is insensitive to a perturbation of psi of the distances. Let me take a few examples. So in this example, in the left figure, I have 4 points and the pairwise distances between the points are also given. So let us consider the k-center clustering problem for k equals to 2 and r1 equals to 10. Then we can select two balls of radii 10, one centered at A and another centered at B. And these two balls cover all the points. So we obtain clustering where the clusters are AC and BD. And note that this clustering has dilation exactly 1. And as the distances are at least 10, the optimal dilation must be at least 1. And hence, this is the optimal clustering, and it is not hard to see that it is a unique optimal clustering. Now, the question is this instance two perturbation resilient? And to see that, consider the separation between the two clusters, A and C and BD. And all the distances are 50 across these two clusters. So if I consider any two perturbation, then after that, the distances must be at least 25. It cannot be less than 25. However, if we consider the distance between A and C and B and D, they are 10. And after any such two perturbation, they can be at most 20. Thus, even after such a two perturbation, A and C and B and D are closer compared to any other pairs of distances, and hence it's beneficial to cluster A and C and B and D together, and we obtain the same optimal clustering. So in this case, the instance is two perturbation resilient. However, if we consider a slightly different instance, so which is shown on the left. Here also we have 4 points. However, we have different distances. The optimal clustering still remains the same, AC and BD. However, this instance is not too perturbation resilient. One can consider the perturbation shown in the right figure, where the distance between A and B is 25, C and D is 25, and all the other distances are 30. So in this case, it is beneficial to cluster A and B and C and D together. So we obtain different clustering AB and CD, and it is not hard to see that this is the optimal clustering for the modified instance, and hence we can say that the original instance is not too perturbation resilient. These instances are bad instances in our case, and we will assume that these instances do not appear. Now, let me give you some motivation for perturbation resilience. Note that in an actual clustering problem, we are given a collection of objects that we would like to cluster. Thus, we need to come up with a measure of similarity or dissimilarity between the objects at first. And this notion of similarity is captured by a distance function. However, it is not easy to find the true distance function between the objects. So we use a heuristic distance function and hope that we can still retrieve the natural clustering using this heuristic function. But then we have an implicit assumption that any optimal clustering is insensitive to a small perturbation of the distances. And the Pierre condition is a formal way of making this assumption explicit. Subsequently, we study the NUKC problem under perturbation resilience, and we obtained the following results. So first, we show that the problem can be solved in polynomial time under only 2 perturbation resilience if we have only a constant number of radii classes. And note that if we have a single radius class, that is for K center, the problem is still NP hard without perturbation resilience assumption. In the special case of K center and other popular clustering problems, polynomial time algorithms were already known for the problems under perturbation resilience. In the general case, we showed that perturbation resilience doesn't help. In particular, we show that for any gamma and psi, the problem under psi pair is hard to approximate within a factor of gamma. And this holds even in tree metric and the Euclidean metric of dimension 1. In the rest of the talk, I will discuss the polynomial time algorithm for constant number of radii classes. And this algorithm is based on a well separation lemma, which is as follows. So let us consider the optimal clustering, and in particular an Ri ball and an Rj ball in the clustering, such that Ri is at least Rj. Then for any point in the Ri ball and any point in the Rj ball, the distance between these 2 points must be strictly greater than Ri. So the separation between the Ri ball and Rj ball must be greater than Ri. This lemma follows from the definition of 2PR. However, it's not straightforward to prove this lemma. In the interest of time, I skip the proof and instead discuss how to use this algorithm, how to use this lemma to obtain the algorithm. And let us consider the K-center problem at first. where we have the same radii, and assume that the optimal dilation is exactly 1. So in case of K-center, the separation between the optimal clusters are more than R1. So in this figure, I have shown the clusters by blue stars, and the separation between the clusters are shown by the green edges. So the green edges must have weight more than R1, and the blue edges have weights at most 5. And in this case, the algorithm is pretty simple. We considered the complete graph on the points where the weight of each edge is the distance between the corresponding points. And what we do is we remove all the edges which have weight more than R1 from this graph. So we are left with a collection of connected components, and we cover each connected component by a single ball of the minimum radius possible. To see the correctness of this algorithm, let us consider the optimal clusters. And we know that they are separated by more than R1 distance. So if we remove the edges from the complete graph, then all these clusters become disconnected. However, if we consider one such cluster, that cluster remains connected. This is because the distance between any point in the cluster from the center is at most R1, and we do not remove those edges. And thus, in this case, the connected components are corresponding to the optimal clusters, and hence we obtain the optimal clustering. And this algorithm can be trivially extended for constant number of radii classes in the following way. So what we do is, at first we remove the edges which have weight more than R1. So we get a collection of, say, ill-connected components, and we know that K1 of them are corresponding to the R1 clusters, but we do not know which ones. So we again apply the same process. We remove more than R2 edges from these connected components to obtain another set of connected components. And we know that K2 of these are corresponding to the R2 clusters, as the R2 clusters are now separated from the other clusters. And we repeat this process constant number of times for all the classes to obtain a component tree which has height C, that is the number of radii classes. And the problem that we need to solve on this component tree is to select K1 vertices from the first level, such that for any such vertex, if I place a ball of radius R1 at that vertex, then all the descendants must be covered. Or in other words, by placing one R1 ball, I can cover the whole component corresponding to that vertex. And similarly, we need to select K2 vertices from the second level, K3 vertices from the third level, and so on. So in our case, the problem boils down to the following problem, where we need to select vertices from all the levels, such that if we consider any leaf to root path, then at least one non-root vertex must be selected from this path. And this ensures that all the points in the leaf are covered, and as all the points appear in some leaf, we can make sure that all the input points are covered by the selected balls. So this problem is basically the firefighters problem, and this problem can be solved in polynomial time. for trees with constant height. And hence we obtain a polynomial time algorithm. So in summary, we showed that the NUKC problem under two-perturbation resilience can be solved in polynomial time if we have constant number of radii classes. However, we showed that in general, perturbation resilience doesn't help. Many open questions remain. One such interesting question is to obtain a constant approximation for 3 radii classes. Another open direction is to study the parameterized complexity of this problem. With that, I conclude this talk, and thanks for listening.